move forward with the chapter 1. As we know that nearly 40 to 70% drugs are poorly soluble, hence making the formulation difficult. So BCS gave a classification system based on solubility and permeability, and it has four different classes. The class 1 is high solubility, high permeability, second is low solubility, high permeability, third is high solubility, low permeability, and fourth is low solubility and low permeability. So, what is class 1? These drugs are well absorbed and have very high bioavailability, but they have a problem of dose jumping. So, it can be solved by using techniques like controlled release formulations, entry coated tablets, and matrix formulations. Second is class 2 drugs, which have good permeability, but they limit their in poor solubility. And this can be tackled by using micronization, amorphous solid dispersion, and complexations. Class 3 drug which have high solubility but they lack in permeability, hence they have problem in crossing the intestinal membranes, and it can be solved by using prodrugs, penetration enhancers, or nanoparticles. The class 4 drug is a very challenging because it has problem of both low solubility and low permeability, but this can also be rectified by using suitable formulations and developing it by lipid-based formulations, cyclodextrin complexes, and nanoemulsions. So, according to BCS classification, solubility can be defined as a drug substance which is highly soluble if single therapeutic dose is completely dissolved in 250 ml or aqueous media over a pH range of 1.2 to 6.8 at 37 degree Celsius. Permeability is defined as the assessment of permeability, which should be preferentially based on extent of absorption derived from human pharmacokinetic studies, that is, absolute bioavailability. And they also define that if a drug has permeability greater than 85%, then it is been classified as highly permeable drug, and it can also be accessed by using Kekoto cell lines. Now we are clear with solubility and permeability. So these both are interrelated, and if these both are less, means low solubility and low permeability, so we can say that it will also have bioavailability problems, or they will be lacking in bioavailability. So what is bioavailability? It refers to the extent and rate at which the active moiety enters through the systemic circulation and accessing the site of action. So, what are types of bioavailability? The first one is in vitro bioavailability, wherein we calculate the amount of the drug in vitro under a simulated physiological conditions, and it can be calculated by amount of the drug dissolved in test solution divided by total amount of drug in test formulation multiplied by 100. The second one is in vivo bioavailability, where we measure ADME of living organism. The calculated formula is AUC of drug in plasma divided by AUC of drug after IV dose. So we move forward to reasons of viability. The first one is insufficient time of absorption and dissolution, partition coefficient, first pass metabolism, poor aqueous solubility, effect of efflux pumps, and low permeability. We move on to the first one, insufficient time of absorption and dissolution. As we have said that if the drug is rapidly eliminated or cleared, then it don't have time for contact with the membranes. For example, here we have taken intestinal wall. So if it doesn't have sufficient time, then it won't be absorbed. Second is insufficient dissolution. As we have talked in BCS classification also, okay, if the drug is poorly soluble, then it would have problems in dissolving in the GIT also, even if it has good permeability. So, good dissolution can be good, but if it is not good, then it is a rate limiting step for many of the drugs and absorption processes. Next is partition coefficient. We know that our whole body is consisted of hydrophilic as well as lipophilic, but most of the part is hydrophilic. So we need to have the value of partition coefficient in between to 1. If it is too lipophilic, then it will be retained in the cell membrane. It won't pass forward. The first pass metabolism, as we know that liver is the organ where the first pass metabolism occurs, as many of the drugs are metabolized in the liver and before it goes into the systemic circulation. So this reduces the viability of many drugs. So why does it goes under first pass metabolism? The first is the drugs are very lipophilic in nature. So They are metabolized by liver. Then second is the drug is a substrate of cytochrome P450 enzymes, or if the drug has been administered orally. Then poor aquasolubility. So when a drug is being poorly aquasoluble, it means that it won't get dissolved in bodily fluids. Another factor is low permeability. If a drug is having low permeability, that means it can't pass effectively in the intestinal membrane. Hence, high permeability is associated with better viability for oral drugs. So it can easily cross barriers. Next comes drug efflux pump. Now, one of the main drug efflux pump that reduces the viability is PGP, as it leads to the lower drug levels in the bloodstream and reduce effectiveness of the drug. So, in that case, we have to provide more amount of drug, which could lead to toxic effects or side effects. So, the main reason of viability we can highlight is the first one is poor or low aqueous solubility, second is low permeability, and third is effect of PGP like efflux pumps. So, how can we enhance this type of viability or problems related to viability? So, these are problems that is poor aqueous solubility, inappropriate partition coefficient, first pass drug efflux, low permeability, and degradation of GIT, as we have discussed everything earlier. So, what are techniques to improve viability? The first is particle size. It is a very old technique. We all know that in that we are reducing the particle size and providing some of the other drug forms, that is polymorphism, salt or crystal formation, micronization, nanonization. Then modification of crystal habit, where we use crystal engineering, form hydrates or solvents or a stable polymorphs, which will uh, change the crystals. Then we move to solid dispersion, where we have hydrophobic matrix and a hydrophobic drug. So here we take a carrier system to deliver a hydrophobic drug. Then comes eutetic mixtures. We all know that when two compounds are mixed, they do not show or offer generate a new entity, but at specific fractions, they prevent crystallization, which will result in a lower melting point systems, and either they have two starting components. So the first one is poor aqueous solubility, second is inappropriate partition coefficient, which can be improved by techniques like SMEDS, self microemulsifying drug delivery system. Self nanoemulsifying drug delivery system means they consist of oil, surfactant, and co-solvent. Then comes liposomes. We all know liposomes. They are spherical lipid vesicles and they have lipid bilayers, so it can increase the efficacy of therapeutic index and of the drug. Then we move on to pH adjustment, where we can adjust the pH of some of the drugs and the systems that can enhance the poorly viability and solubility problem. Then we move on to ester formation, wherein we introduced an ester group by the reaction of alcohol, and this process typically results in formation of ester linkages, and it can be also known as ester prodrug. Then we move on to first pass effects, wherein we can change the formulation of the dosage form, wherein we can move to a new dosage form. Prodrug, as we already discussed. Novel drug delivery system like microemulsions. We know that microemulsions consist of oil, water, and surfactant. Typically, they are transparent or translucent, and the particle size range from 10 to 300. SMEDs, which has already been discussed earlier in the previous slide, solid lipid nanoparticles. We know that they are organized in specific drug delivery system, biodegradable and biocompatible with a size range of 50 to 1000 nanometer. They also have a solid hydrophobic phospholipid coating. So they can transport both the drugs, hydrophilic as well as hydrophobic. Now we move on to drug efflux pumps. So many drug efflux inhibitors can be used to inhibit these pumps and increase the bioavailability, as we know that these pumps efflux out the drug. So we don't want our drug to be effluxed out. So what we do is we inhibit the pumps like PGP and give some PGP inhibitors to inhibit the pump. So the viability of the drug can be enhanced. Then we can use prodrug, as we have discussed earlier. Low permeability problems can be solved by SMEDs and SEDs, liposomes, and penetration enhancers. Degradation in the GIT is very well known approach where we can use entry coating or colon targeted drug delivery system to stop degradation in the GIT. So what can we conclude from this study? That poor viability can be have two reasons, that is low solubility and low permeability, which can be solved by using solubility enhancement technique including solid dispersion, lipid crystals, co-crystals and prodrug, and low permeability problems can be solved by inhibiting PGP efflux pump. So what is PGP? PGP is polyglycoprotein where P stands for permeability. It is a member of ATP binding cassette ABC transporter superfamily, and it acts as a physiological barrier, right, by removing harmful and foreign substances from cells. As they don't know that drug is a useful substance, they will also act by throwing out the substances as a foreign substances, where it can also alter pharmacokinetics of various drugs, as I said earlier. So, due to the selective distribution at the port of entry and exit, PGP has been speculated to play a major role in absorption, distribution, and excretion of many xenobiotics and drugs. So, here is the structure of PGP where it has 28 amino acid chains. It has two domain, transmembrane domain 1 and 2. It has N terminal and C terminal. The white dots are showing phosphorylation sites and the black dots are showing positions of PGP mutations. So the phosphorylation sites are important where the drug can go and bind. So what is mechanism of PGP? Now, first of all, the drug molecule will enter in from the cytosol. As we can see in the video, it is entering in the cytosol. The drug, after entering, the ATP will be binding to the PGP pump and hence they will throw the toxin out of the cell. Now here the whole process is ATP dependent. So without binding the ATP, we can't go for throwing out the drugs or the foreign substances. So as we can see in the video, this is a PGP pump showing, and the silver one shows the drug active sites or pockets, and the pink one shows that it is a drug. Yes, the pink one which is highlighted shows the drug. Silver one, as I told, it is a drug binding pockets. So here the drug is going and attaching at that site. And here, as I said, ATP will be binding to that and throwing the toxins out from the inside cells or membranes. So how PGP is expressed and where in which parts of the body it has been expressed. So we can see that the first is liver, where it has been expressed in bile calculus. In brain, it is in brain parenchyma. In kidney, it is in nephron. In intestine, it is in the wall. The main example is there. The tumor, it is in tumor cells. Then in placenta and in testes. So majority of the sites have blood or walls. So we are clear with what is PGP. And as I told, if we want to increase the viability, we need to have stoppage of that action. So how we can do it? So by providing some of the inhibitors which will inhibit the pump. As we can see in the first diagram, where we are blocking is the when the drug is been efflux out of the membrane, that side can be blocked by PGP inhibitors. So how PGP inhibitors work? So there are mainly three mechanisms. The first is competitive or non-competitive mechanism. The second is binding with the ATP, and third one is efflux of substrate through the central port. So inhibition of substrate. Okay. So what are PGP inhibitors? As we have seen, they block the PGP efflux pump. So the class, this describes the class of PGP inhibitors, the first generation, which were found to be highly toxic, and these are chemical moieties that include verapamil, nifedipine, cyclosporin, reserpine, ibuprofen, quinidine, tamoxifen. The second generation, which were potent but less toxic than first generation, that includes dexverapamil, valproder, and chinconin. The third generation were very superior and balanced novel molecules that include teriquidar and elaquidar. Hence, we can prove that these PGP inhibitors, they are all synthetic and they all are having other effect, pharmacological effect. So they have a wide variety of probably chances of toxicity. Also, they are substrate to one or another sites. So here, what we can say is that we can develop natural PGP inhibitors which will not have side effects on the body, and plus they are pharmacologically not much active as this moieties, hence they are considered as more safe. So these examples include black pepper, ginger, green tea, drumstick, and citrus fruit. So black pepper, as we can see here, it has improved bioavailability of many medications such as sulfasalazine, rifampin, phenytoin, propranolol. Then ginger, which increases bioavailability of many antibiotics such as azithromycin, erythromycin, cephalosporin, etc. Then green tea, which have proven to increase the bioavailability of nadolol. Then the next comes drumstick, which have been increased the bioavailability of many drugs like rifampicin, tetracycline, ampicillin. Then citrus fruits like orange, the main constituent is quercetin. So it has also been improved the many uh, improve the efficacy of many drugs, that is the diltiazem, digoxin, and epigallocatechin gal.